So today's lesson is on the universal law of gravitation. So let's talk about that. So what we learned last lesson was that Kepler devised a mathematical relationship describing the motion of the planets, but the big problem was it was in astronomical units and Earth years, and it didn't really work for everything, because if you're talking about a star orbiting a black hole millions of light years away, it doesn't work as well for that. So what Newton did is he used this idea that Kepler came up with, and he developed a law that not only covered all planetary objects and their motion in space, but the law meant to cover all objects in the universe. So it's incredible. The power of this law cannot be overstated. From planets and stars to atoms and molecules, everything in the universe with mass is covered by this law, and that's why we call it the universal law of gravitation. So what his law is about is you have two masses. So it has to do with the mass of mass 1 and the mass of mass 2 and the distance they are away from each other. That was his idea. So he came up with this idea, he came up with this relationship, and Newton was a theoretical physicist. So theoretical physicists come up with ideas and mathematical equations, and it's up to experimental physicists to test if these ideas actually work. So the experimental physicist that came up with an experiment to test this idea his name was Cavendish. And Cavendish came up with an experiment that looked like this. So in the experiment, you have two lead spheres, and you use lead because it's really dense, so you don't need to make it that big, but it can be really, really heavy. And on the other side are just counterweights. So actually, these are the two lead spheres that we're looking at, and these are counterweights on the other side. And then you shoot a beam of light. This one shows a laser, but there weren't lasers in this time, but you can do the same thing with just a beam of light. You shoot a beam of light at a mirror, and what's going to happen is these two masses are going to attract each other, and as they attract each other, it's going to bring this one towards it, and as it does that, it tilts this mirror here, and it's going to cause this laser to bounce off, and it reads a degree of twist. So how much it twists. And this fiber, this cable that's being held up by is not just any cable. It's a special fiber called a torsion fiber, and it's calibrated so that when it twists a certain amount, you can relate that to a certain amount of force. So if it twists 10 degrees, that might be 200 newtons of force. 15 degrees might be 400 newtons of force, right? So we can take a look at this experiment and what it looked like. So these two masses attract each other, you bring it closer, and you can see now it's attracted. It bends that beam of light, and you can read how many degrees it twisted. Okay. So what Cavendish did in his experiment is he manipulated three different things. So the first thing that he manipulated was mass 1. And what he was testing was what that angle of twist was. Right? And from that angle of twist, you were able to find out a force, right? So angle of twist or force would be the correct answer, because from the angle of twist, you can look up what's the force. And then he did another experiment where he manipulated mass 2. So how does mass 2 affect it? And it's going to be the same thing for the responding variable. He wanted to measure that angle of twist or the force. And then the last one, he manipulated the radius between them. And he measured that angle of twist or the force. So mass 1, mass 2, and radius were the three different tests that he manipulated, and it's important that you only manipulate one thing, because if you manipulate more than one thing, you can't tell what actually affected your responding variable. So it's really important to control mass 2 when doing this experiment, and your radius, right? Only want to control one, and then, or manipulate one. And for this one, mass 1 and the radius would be the controlled variables. And for this one, it would be, not radius, it'd be mass 1 and mass 2 that you'd want to control. Okay. And then after you do an experiment, you graph it out. So after getting the data from his experiment, Cavendish graphed his data. And when he graphed FG versus M, he got a nice straight line graph. And what that tells us is that FG is directly proportional to mass 1. And then he did the experiment with mass 2 and got the same results, and it told us that Fg is directly proportional to mass 2. And then he graphed out his data from Fg versus R, and he got a curve like this. So what that tells us is that this type of graph is an inverse graph. So Fg, force of gravity, is inversely proportional to radius. And if he just inverse the values, he didn't get a straight line with his graph. So what he did is he inverse squared them. And then when he did that, he got a straight line. So that tells him that they have an inverse squared relationship. So then what he would do is he'd take mass 1, mass 2, all divided by r squared, because they're on top, because they're directly proportional. These are inversely proportional, and he got a straight line. So no matter what mass 1, mass 2, and the radius were, he tried this experiment hundreds of times, and then he graphed out this last one. He always got the same graph. He always got he always got the same slope. He always got 6.67 times 10 to the negative 11 as his slope, no matter what it was. So what this tells you is that, well, the 6.67 times 10 to the negative 11 must be a special number, right? It's what we can relate it to is that area of a circle is equal to pi r squared. So if I did a graph of area of a circle versus r squared, and I graphed it out, no matter what areas I used and no matter what radiuses I used, I would always get 3.14 as my slope no matter what, right? Because this is y, and then my x is r squared. So my slope is equal to pi every single time. So this number here is kind of like pi. It's a constant, it's a special number, and we need that as part of our formula. So this is our universal law of gravitation formula, where Fg equals g m1 m2 all over r squared. And because this is a force, you can find this in the force part of your data book. So Fg is force of gravity, m1 is mass 1, m2 is mass 2, r is the distance between the two masses in meters, and then g is our universal gravitational constant, which is 6.67 times 10 to the negative 11, which you can find on your data book. Here, let me open up the data book. So the formula is right here. Sorry, I can't switch it because it opened up in Internet Explorer. I can't make it the other way. So this is our Fg formula, and you can find this universal gravitational constant right here on the back of our data book. So you don't have to memorize that. But what you can do is you can store that value in your calculator. So I'll show you how to store it in there. Let me make this a little bit bigger. So if you want to store a number, so we want to store 6.67 times 10 to the negative 11 into our calculator. So you type in the number just like that, and you push this button here, which is the store button. And if you push alpha G, because that's the symbol for it, is G, and then push enter, it'll be stored as G. So now when we type that in, we can just go, if we want to go G times 2, right? It knows that G is 6.67 times 10 to the negative 11, and we're multiplying it by 2. So you have that stored in your calculator now. Oh, this example doesn't really work. So as you may have noticed, there's a strong force of traction. So usually I pick 2 students in class, but we can't do that with this example. So there's a strong force of attraction between, let's use Mr. Pandos and, let's say, me. We're buddies, we're friends, we text each other. So Pandos has a mass of, let's say, 50 kilograms. And Latte has a mass of 70 kilograms. So we can calculate the force of attraction between them. Okay. Pandos is, I'm in the library still, so Pandos is working upstairs. So I'd say the distance between us was about, I don't know, we're about 12 meters apart. So we can use our new formula, Fg equals G, m1, m2, all over r squared, where G is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Okay, so mass 1, it doesn't matter who mass 1 and mass 2 is. So mass 1 is 50 kilograms, mass 2 is 70 kilograms, and we're a distance of, what did I say? Let's see, we're 15 meters apart right now. We have to remember to square that. So we can type that into our calculator. So on top, I just have to go alpha g for that 6.67 times 50 times 70, and then divide it by 15 meters squared. So I wonder if we're going to have a strong force of attraction. Oh, that's a very weak force of attraction. So 1.0 times 10 to the negative 9 newtons is our force of attraction between each other right now. So why is that number so small, right? And you can see it's so small because we're always multiplying it by 10 to the negative 11. So this makes it really, really small value for a force of gravity between things with small masses. And this is actually a really good thing, because if this number was a lot bigger, then everything would be attracted to each other. You'd be walking to the hallway and like a big kid would walk down the hallway and everyone would be gravitationally attracted. So it's really good that this number is small, so it doesn't affect smaller things, but it's good that it's not too small that it keeps our planets orbiting the sun, right? So we don't go into outer space and life wouldn't exist. So this number is a nice Goldilocks. It's just right. It's not too hot, not too cold. It's perfect. So calculate the force of gravity on a 100-kilogram man on the surface of the Earth. So on the back of our data booklet, we have this G value, and we also have data on the Earth. We have the radius of the Earth and the mass of the Earth and the orbital radius of the Earth. We'll talk about orbital radius later, but we'll talk about these two. So if a man is standing on the surface of the Earth, we always want to measure our distance between the centers of each mass, right? So the radius between them would be the radius of Earth, right? Mass 1 would be our person, our man, and then mass 2 would be our Earth. So we can calculate this. So G, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Mass 1 is the mass of our man, which is 100 kilograms. And the mass of our Earth from the data book is 5.97 times 10 to the 24 kilograms. So this is a really big mass, so it's going to have a stronger force of gravity, right? And then our radius between them would be the radius of Earth, which is 6.37 times 10 to the 6 meters. Don't forget to square it. So if I plug all of that in to here, you can go alpha G times 100 times 5.97 times 10 to the 24, and then we divide it by 6.37 times 10 to the 6, and square it like that. We're going to get 981. Right? How did I know that? Well, the reason that I knew that is because Fg equals mg, right? If we go 100 times 9.81, because he's on the surface of the Earth, we're going to get 981 newtons. So both of these Fg's are the same. The difference between these two formulas is if we know what the acceleration due to gravity is, well, we should use this. If we don't know the acceleration due to gravity, then we can use this, and it opens it up to a lot more situations where it isn't 9.81, which is really helpful. So calculate the gravitational force between two identical objects 0.1 meters apart, and that's their force between them. Determine, or not calculate, but that is the gravitational force. Determine the mass of each object. Okay, so I added this because this confuses people. So the way the question is set up, we don't know mass 1 and we don't know mass 2. But it does tell us information. It says that the two objects are identical. So if the two objects are identical, calling it mass 1 and mass 2 isn't necessary because they're both masses. And if we go mass times mass, then we can just call that mass squared. right? If we rearrange this, we can find out what the mass is. So we just go 0.1 meters squared. I'm just going to switch my pen, times the force of gravity, which they gave us in the question, 2 times 10 to the negative 5 newtons, all divided by 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared, all square root, and we can get our answer. So let's plug that in. 0.1 squared times 2 times 10 to the negative 5 divided by alpha g, and then we can square root it. So each mass is 55 kilograms. Okay. So this term in our data booklet, orbital radius and radius. So this is radius here, and this is orbital radius. So this is on the back of our data booklet as well. So radius is if I have a planet. So this is my planet, and this is the radius of the planet. So for example, if this was Venus, the radius of Venus is 6.07 times 10 to the 6 meters. Orbital radius is when you have the sun and then you have Venus here. Orbital radius is measured from the center of the object to the center of the object. So how big is the orbit? So this is going to be a lot bigger, 1.08 times 10 to the 11 meters. So it's really important to know the difference between radius and orbital radius, and we'll practice when do you use radius and when do you use orbital radius. Okay, so find the force of gravity the sun exerts on Mercury. So pause the video, try this on your own, use that data from the back of your data booklet, and see if you can figure this out. So this question doesn't actually give any numbers because all the numbers are in the back of your data booklet. So we want to find the force of gravity that the sun exerts on Mercury. So we can draw a little picture. Here's sun, here's Mercury, right? We want to know the distance between these two objects. So that's going to be the orbital radius. We want the orbital radius as their radius, right? Because we're not standing on Mercury or anything like that, like the last question. So we can plug in our numbers. 6.67. Oops. Sorry, I was on the wrong screen and I was doing all that stuff. That's our formula. This is a picture that I drew Sun and Mercury, and we want to find the orbital radius. So we can go 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Mass 1 is going to be the sun, so we'd have to look that up in our data booklet. So the mass of the sun is 1.99 times 10 to the 30 kilograms. And then mass 2 is going to be Mercury, and if I look that up, that's 3.2 times 10 to the 23 kilograms. Okay. And then we need the orbital radius in between them. So we want the orbital radius of Mercury, because it always measures from the sun, except for the moon measures from the Earth, because the moon orbits the Earth. So Mercury to the sun is 5.8 times 10 to the 10 meters squared. So I plug all that stuff into my calculator. Alpha g times 1.99 times 10 to the 30 times 3.2 times 10 to the 23, all divided by 5.8 times 10 to the 10 squared. And I get the force of gravity the sun exerts on Mercury to be 1.26 times 10 to the 22 newtons. Okay, so all that we got from data in our data booklet, so you got to know how to use that. Okay, so this is another type example that we can see. So 3 masses are arranged in a line as shown. So draw a free body diagram of the forces acting on the 100 kilogram mass. Okay, so all these objects are going to attract each other. So it's really important to not get confused in your head is if you say that these two masses are locked into place, because we're not trying to find the force of gravity on these, we're just trying to find the force of gravity on these. So these are little clips, and they lock it into place. The next thing you need to do is draw a free body diagram of the forces acting on the 100 kilogram mass. So the 100 kilogram mass is going to be attracted to the 60 kilogram mass. So let's call these 1, 2, and 3 so we can label them. So this is the force of gravity from mass 3. Right? It's going to pull it that way. So it's also going to experience a force of gravity towards mass 1. And it's important to think about, is it going to be bigger, smaller, or the same size as the force of gravity from 3? So we have G, mass 1, mass 2, all over r squared. Right? So we can see that this one has a bigger mass. Right? So the mass is bigger, but the radius is bigger as well. Right? So the mass being bigger makes the force of gravity bigger, but these have an inverse relationship. So the radius being bigger makes the force of gravity smaller. Right? So what's going to have a bigger impact? Well, this radius is squared, so that's going to have a bigger impact. So because this mass is closer, even though it's a smaller mass, I am guessing that it's going to have a bigger force of gravity. So this will be force of gravity 1. We're going to expect it to be bigger. Okay, so let's determine the gravitational forces acting on the 100 kilogram sphere. So we need to do this as two separate equations. We can't do this as one. So we need to find Fg3 and we need to find Fg1 separately. So Fg3, let's actually call this 2 and 3 over r squared. That's how we're gonna use the 100 kilogram mass and mass 3. And then to find Fg1, we're gonna use, oops, going too far over. We're gonna use mass 1 and mass 2 all over r squared. Okay. So 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared times our mass 2, which is 100 kilograms. So this is the force of attraction between the 100 kilogram mass and the 60 kilogram mass. They are 15 meters apart. And we have to square that. The other one is 6.67 times 10 to the negative 11. And mass 1 is 40 kilograms. And I want to find the traction between the 40 kilogram mass and the 100 kilogram mass. The radius between those two is 10 meters squared. So I'm going to type that into my calculator. Alpha G times 100 times 60 divided by 15 squared. So that's the force of attraction for the 3. So I said that I expected 1 to be a little bit bigger, so let's see if it is a little bit bigger. So if I push second enter, it just types in the last thing I typed in. So I want to find between the 100 and the 40 kilogram mass, and then they're 10 meters apart. Just to save myself a little bit of time, and yeah, it's a little bit bigger, right? Just a little bit bigger than the first one. Okay, so from here, what that means is we have our mass 2, which is our 100 kilogram mass. It experiences force of gravity 3 that way, and a bigger force of gravity 1 that way. We have two forces acting on an object. We've done this before. We can find our net force. Our net force is just going to be, this one's bigger, so I'm going to make this positive, this negative. Fg1 minus Fg3. So to find my net force acting on them, I just have to take this number and subtract it from 1.77866666666 times 10 to the negative 9. And I get that. That's my net force. It is positive 8.89. I only have 2 sig digs, so 8.9 times 10 to the negative 10 newtons. And because it's positive, and I said positives to the left, we'd want to add that vector to there. And I would say 8.9 times 10 to the negative 10 to the left. Okay, not too bad. Okay, so I want you guys to try a board question. I want you to start off by drawing a free body diagram of the forces acting on the 60 kilogram mass. Okay, so this time we're locking these ones into place, and we want to find the forces on this. So start off with your free body diagram. We'll call this 1, 2, and 3. Okay, pause the video and then see if you can do that, and then I'm going to go to the next step. So pause. Okay, so both of these would be attractive forces. So the 60 would be attracted to FG2. So this would be FG2. 2 would pull it towards it, and 1 would pull it towards it as well, but is it going to be bigger, smaller, same size? Well, it's so much further away. It's going to be, actually that's not even a good drawing. It's going to be, ignore that. It's going to be way smaller. So this is FG1, right? FG1's not going to pull as hard because it's further away. So if we want to actually calculate those values, it's the same idea as the last question. It's just different numbers. So let me draw out that picture. So we have 40, we have 100, and we have 60, like that. And then this is 10, and then this is 15 meters. Right, so we have this big FG2 and this small FG1, like that. So if I want to find FG1 this time, same formula, same G, but I want to find out, so this is mass 1 and this is mass 3. I want to use mass 1 and mass 3, so it's going to be 40 and it's going to be 60, and then they're going to be 25 meters apart. Okay, for this one, I'm finding the force of attraction between these, so it's still 160 and they're still 15, so that's going to be the same value there. So if I do this in my calculator to finish it off, so I can bring up that answer from before. So this is going to stay the same. The one that's going to change is I want to find the force of attraction between the 40 kilogram mass and the 60 kilogram mass, and they're 25 meters apart. Right? And according to our free body diagram, both forces are in the same direction, so we just have to add those together to find the net force, right? They're both going to the left, so we would add this to 1.77866666 times 10 to the negative 9, and then this should be our net force acting on it. Okay. Okay, and then the last one is just a 2D question. So all the masses are 100 kilograms. Determine the net force acting on mass 2 if the other two objects are stationary, right? So these ones, this is locked into place, and this is locked into place. So we start off, you always have to start off with your free body diagram. So this would be FG3, right? 2 would be attracted to 3, and 2 would also be attracted to 1. And it's a little bit further away, so it's going to be smaller. So this is FG1 like this. Okay. So we can calculate FG1 and FG3. So let's do that. So again, same formulas. So if we want to find FG3, it's going to be 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Both masses are the same, so I can just go 100 kilograms squared because that's 100 times 100. And then 2 and 3 are 5 centimeters apart. I have to make sure that's in meters, and I have to square it. For this one, it's 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. And again, they're 100 kilograms squared, but these ones are 8 centimeters apart. Okay. Plug that in to my calculator. So I'll go alpha g times 100 squared, close my bracket, divided by 0.05 squared, close my bracket like that. So that's the first one, and then the second one, it's exactly the same, but they are 8 centimeters apart. Okay. Good, so those are my two values. So according to our free body diagram, FG3 was like that, and FG1 is like that. So we can't just add them together because it's a 2D question. So what we need to do is we need to add those two vectors tip to tail. So FG3 is like this, which is 2.668 times 10 to the negative 4 newtons. And then FG1 is like this, which is 1.04 times 10 to the negative 4 newtons. So to find the net force, I need to find that there, which means I have to Pythagoras these two numbers, 1.04 times 10 to the negative 4 squared plus 2.668 times 10 to the negative 4 squared, all square root, and I can find out what that is. So let's do that. So I'll take this squared plus 2.668 squared, and I'll square root the answer. Oops, I just did 2.668. Oops. Shoot. Let's try that again. Okay, that's the first one. And then this is the second one. Sorry, this is an old calculator, so I can't just grab the answers. Okay, so let's do that squared plus 2.668 times 10 to the negative 4 squared, and then I'll square root my answer. So I get the net force to be 2.86. There's only one sig dig, but whatever, that's a screw up on my part. So that's the net force, right? And then we also need an angle. So we'd have to go tan negative 1 of opposite over adjacent, so 1.04 times 10 to the negative 4 over 2.668 times 10 to the negative 4. So I'll have to tan negative 1 those. And I get 21 degrees. So this is 21 degrees. And I'm not going north, I'm going west of north. That's my final answer. Okay, so that's how you do 2D questions. Okay, that's all for this lesson. So this is your homework. Give it a go and let me know if you have any questions about it.